Hello everyone, just give me 1 second. Let me know if my audio and video is clear. Then we will start. Is my audio video clear, guys? Yesterday no one told me. I realized later that my audio was not very clear. It was very low. I checked the class afterwards and the audio was not very clear. Huh? Was it the case? चलो स्टार्ट करेंगे आज नेक्स्ट सेशन. तो yesterday we discussed many things. What did we discuss yesterday? We discussed basically why we need to study thermodynamics. Okay, what is the importance of thermodynamics? Importance of thermodynamics. What role thermodynamics subject plays in your GATE exam, in your PSU interviews, and your basically MTech, MSc, all these programs. Okay, so basic and applied thermodynamics. Then we have seen the weightage of this subject in GATE exam. Around कितना है? 12 to 14 marks out of 100. ठीक है. Then we have discussed in very detail what are the reference material that you should use, and specifically for except the books, all the reference material will be valid for all your subjects. Presentation notes, your particular notes, okay, GATE previous year question, ESC previous year question, those are valid for each and every subject. Only the books are different, which I have told you, but those reference material is valid for each and every subject. Okay. Then after that we have talked about GATE official syllabus. And finally, we have talked about what we are going to cover. What we are going to cover. Ajmira, good evening. Good evening. Kal nobody told me that my audio was not very clear. I saw it in the class later on. When I see the recorded class, I realized the audio was not very clear. I think it is clear now, right? Are you able to listen properly? Chalo. And finally, we have discussed all the topics and subtopics that, okay, today you joined, ठीक है, fine. Topics and subtopics that we are going to cover. We will cover. Okay. So I have told you almost 70 to 80%. Few topics were missing here and there, but whatever I remembered, I told you the entire topics of thermodynamics which we are going to cover. So these are the things that we covered yesterday in detail. Today we are going to move ahead with the basic introduction to thermodynamics. Okay, chaliye. Before we start, let me give you a brief introduction about myself. So I have 6+ years of teaching experience for GATE, ESC, PSUs, and of course AE and JE as well. I have done my MTech from IIT Kharagpur, MSc from Politecnico di Milano, 3.5 years of industry and research experience, international and national research publications, and my area of expertise is basic and applied thermodynamics and heat transfer. Okay, chaliye, very good. So before we start the lecture, guys, few announcements for you. So there is a very important workshop by Abhinav Negi sir on 20th of March, okay, which is tomorrow at 7:30 p.m. It is the strategy that you need to follow for GATE 2025, 7 golden rules. Okay, so you need to join the app, guys, and because on the app there is so much going on that you are missing out. Okay, so do join the app and you can attend so many free sessions there. Okay, then if you are targeting GATE 2025, So there is a scholarship that test that will happen. I think this is already done, but the next one will be announced very soon. You will get from 10% to 90% of scholarship. So if financial constraints are there with you, then still you will be able to claim, no, claim is not the right word, but you will be able to get up to 90% of scholarship. Okay, 10% so you will get anyway. Okay. Already you guys know foundation batch is going on, and we have already covered these subjects. I think Dheeraj sir covered these subjects. Right now I am taking thermodynamics. This is done, and these 3 lectures will be of thermodynamics, and then FM will come. I think Chandrasekhar sir will take this. Okay, so do keep following these lectures. If you have not joined the Telegram channel, join the Telegram channel. You will get the PPT in the Telegram channel itself. Okay, what is the name? Mechanical by Vipin Yadav. You can either search the name or you can scan using this QR code. ओके, चलिए स्टार्ट करते हैं बिल्कुल सिंपल डेफिनेशन से, बिल्कुल सिंपल कि भाई थर्मोडायनेमिक्स, व्हाट इज थर्मोडायनेमिक्स. ठीक है, बिल्कुल सिंपल डेफिनेशन से स्टार्ट करते हैं. सो थर्मोडायनेमिक्स, जस्ट 1 सेकेंड गाइस, जस्ट 1 सेकेंड, गिव मी 1 सेकेंड. So when we talk about thermodynamics, so thermodynamics, as you can see, it is made up by 2 words. What are the 2 words? Thermo plus dynamics. It is made up of 2 words, thermo and dynamics. ठीक है, तो thermo and dynamics. Thermo and dynamics. Now, when we talk about thermodynamics, so thermo means what? When you hear the word thermo, what comes to your mind? What comes to your mind? Thermo means, whenever we talk about thermo, you see therm. So the word either heat or temperature or energy. Basically heat comes to your mind, and heat is what? Energy, a type of energy. And dynamics, so I think you guys know already in very detail. You have seen this word many times. So dynamics is motion. So thermodynamics is made up of 2 words, thermo plus dynamics, यानी कि heat plus motion, या energy plus motion. Okay, sir, okay, ठीक है, energy plus motion. What does it mean? How does energy causes motion? So that is what we study in thermodynamics. So you see, this is your system. Sir, what is system? We will talk about that in some time. But let us say this is something. Okay, your gas, one container is there. Pressure cooker is there. Okay, and you have, it is filled with water molecules. So you have a system. Your pressure cooker is a system, and that has some water molecules. Now what you are doing is, let us say you are giving heat to it. You are giving some heat to the molecules. So what will happen with the molecules? Molecules will start moving. Molecules will start moving in random direction. So they were already moving. They were moving around their mean positions. So all the molecules have internal energy. Because of that, they will be vibrating, they will be translating, they will be rotating. Okay, Avnish, good evening. Okay, so this motion is already there, but it is not very visible with your naked eye. Okay, even if this is my phone, this is my mobile, right? It has some molecules, and these molecules are also vibrating, translating and rotating, but I can't see them. I can't see them with naked eye. Similarly, in water also, water molecules basically they move with, even if it is a steady state condition, it is not moving, but internally they are moving, which you are not able to see. But when you give this heat, this intensity will increase. So it will be visible to you. You see that motion. You see that motion of the water, and it is very visible. If you give it heat, you start seeing that the molecules will start moving from bottom to top, okay? And if you give enough heat, it will start vaporizing, right? So it is very visible to you. That's why I have given the example of water. Even if it is not visible to you, still it is happening. If I start heating this, its molecular energy will increase. Maybe it will not be visible to me, but it will change. Okay. So basically what I am trying to say is, whenever you have transferred some heat, the dynamics, the motion of the molecule has changed. The dynamics or the motion of the molecule has changed. So what has been done here is, heat has caused the motion of the molecule. When you gave heat, it has caused the motion in the molecule. Now, because of this motion, the properties of this system will change. Properties of system will change. Sir, what are property? By pressure can change, velocity can change, temperature can change, volume can change, and there are other properties as well, which I am not telling you right now because you don't know them. But internal energy, enthalpy, entropy, all density, everything will change. Okay. So because of the heat that you have given, it has caused a molecular momentum. It has caused a dynamic action in the fluid molecule. And because of the dynamic action, the properties of the fluid has changed. The properties of the fluid has changed. So when you start studying the effect of this heat on the properties of the system, so that study, that science is called as thermodynamics. So again, what has happened? Heat, dynamics, motion. Heat has caused the motion. Heat has caused the dynamics. Heat has caused the molecular motion, and because of this molecular motion, the properties of the system has changed. The properties of the system has changed. So analysis of this properties of the system while some energy transfer or energy disturbance is happening, that study, that science is called as thermodynamics. Are you able to understand this point? Ki if you are transferring some energy to a system and something is happening internally, yani ki the motion is changing, but because of that motion, the properties of the system is changing. So when you study that how these properties of system is changing, it is called as thermodynamics. Okay. So the scope of thermodynamics is to deal with systems where motion of atoms and molecules of the system is caused by heat or energy. So when you are giving heat or energy and it is causing some motion, molecular motion or atomic motion, so when you deal with these kind of problems, when you deal with this kind of systems, it comes under thermodynamics. It comes under thermodynamics. So it is the branch of science which deals with energy conversion and its effect on the physical properties of the substance. So you see, you have given heat. This heat energy is converted to internal energy of the molecule. This heat, some part of it is converted into internal energy. Now because of this internal energy, what will happen? The property of the system will change. So basically, one energy is converting to another. One energy is converting to another. Okay. So how this energy conversion is happening and how you can do it in a very effective way, and how this change in energy or conversion of energy is going to affect the properties of your system, how these properties are changing, how these properties are changing. Okay, so this is basically this branch of science that we deal with. How one energy is converted to another, how you can efficiently convert that energy, and that conversion, how it is affecting the properties of the system. So when you study all that thing, it comes under thermodynamics. It comes under thermodynamics. Now, what is the objective behind studying thermodynamics? You see, we will study so many things. We will study entropy, we will study irreversibility, we will study reversible process, irreversible process, we will study second law efficiency, all the available energy, all these things. What we are trying to see is how close we are from the ideal process. That means whenever I am converting one energy to another, whenever I am converting one energy to another energy, how I can do it in the most efficient way, how I can reduce the maximum amount of losses, how I can bring the losses to minimum, how I can convert one form of energy into another form in the most efficient way. If you want to study, if you want to know how to convert one form into another in the most efficient way, then you need to know what are the losses, where are losses happening. Okay, if losses are happening, how can I reduce the losses? These things you need to know. Okay, so that is why we study entropy generation, we study entropy, available energy, irreversibility, second law efficiency. All these concepts tells you that how far away you are from the ideal process. Ideal means that this is the maximum efficiency. Now this is your actual efficiency. Now your actual efficiency is less than the maximum efficiency. Now why is it less? Because losses are happening. So we study what losses are happening, how we can reduce the losses. All these things are studied in thermodynamics. How to convert one form of energy into another form in the most efficient way, how to reduce the losses to the minimum point. Okay, so ultimate aim of thermodynamics is to convert the inorganized form of energy into organized form. Now what is inorganized, what is organized, this we will study in second law. We will not study, but just you understand how to convert one form to another. Okay, in the most efficient way possible, in the most efficient way possible. Okay, so this is your thermodynamics. Now, so I told you one thing. What did I tell you? I told you that we try to analyze our system. Okay, so I told you this. Look, you are giving heat, then the molecular motion of the gas molecules are changing. Because of this, the properties are changing. So your aim is to analyze how these properties are changing. Whenever you have given the heat, whatever is happening inside, how it is affecting the system, that we need to analyze. Okay, if I have a system and I give heat, so how it is affecting the system, inside system, how it is affecting. So I want to analyze that. In order to analyze that, I have two approaches. First is microscopic approach. And the second is macroscopic approach. So we'll understand that one by one. So what is microscopic approach? It is also called as statistical thermodynamics. So, sir, what is microscopic approach? as the name is telling you, for example, if you take a microscope, when will you take a microscope? When you go to microscopic level. That means when you go to atomic level, when you go to molecular level. That means you are focusing, by using a microscope, you are focusing on a single molecule. How this molecule is changing. How this molecule is changing. So, see, when I give some heat, so I will focus on only this molecule. I will see how its velocity is changing. I will see how its position is changing. I will see how its energy is changing, and I will record that. Then I will focus on this molecule, how its velocity is changing, how its position is changing, how its energy is changing. Then I will take one other molecule, how its velocity is changing, how its position is changing, how its energy is changing. Okay, so basically what I am trying to tell you is that we are focusing on an individual molecule. We are focusing on an individual when we focus on an individual molecule. Now we all know, if you take for example 1 meter cube volume, then there are millions and billions of molecules. Yes or no? Now if you want to focus on just one molecule, then how these molecules are changing, how the properties of one molecule is changing, it is very difficult to define. Because you see, these molecules, if you focus on just one molecule, it is continuously changing, and there are billions of molecules. So focusing on individual molecule, studying individual molecule, it is very difficult, very, very difficult. So in normal scenarios, we do not use this approach. We do not use microscopic approach. Sir, when do we use microscopic approach? We use microscopic approach whenever molecules are very less. Whenever molecules are very less. Sir, where will be molecules will be very less? When you go to quantum level, atomic level, basically, for example, if you know, like there is a vacuum tube and basically two molecules are striking together and you are experimenting, then you will use this approach, or rare field gases theory. That means basically, for example, if this is a room, I have this room right now, there are billions and 10,000 billions of molecules here. But if I seal this room and I remove all the air from it, all the air, all the molecules I will remove. So I will create a vacuum here. Now whatever machine I bring, I will never be able to create a perfect vacuum. Yes, that means some molecules will be remaining there, like some 10 molecule, 15 molecule will be remaining there. Now if 10, 15 molecules are remaining, even 100 molecules are remaining, I can study those molecules. I can use this approach. So whenever you go to atomic level, or if you go to very high altitudes where pressure is very less, okay, if you go to very high altitudes, pressure is very less. So if pressure is very less, means by pressure is less means number of molecules are less. If in the room 10 people are there, so pressure will be less. If in the same room I bring 50 people, so it will be more congested, more pressure will be there. Okay, so what I am trying to say is that whenever there is a scenario in which number of molecules are less, there you can use this approach. But in normal scenarios, in atmospheric pressure, in most of our scenarios where experiment takes place, by all the engines are working at atmospheric pressure only, right? If I am driving my car, I am driving in this surrounding itself, right? So the fuel is burning at almost atmospheric pressure, right? Or it is, at least it is exposed to atmospheric pressure, or it sucks air from atmosphere, then you compress it to higher pressure. So what I am trying to tell you is, whenever this scenario, normal scenarios are involved, you cannot use microscopic approach because there are billions of molecules. So In this case, behavior of individual molecule is taken into consideration. When you talk about microscopic, behavior of individual molecule is taken into consideration. But I told you that for a gas, each molecule at a given instant has a certain position, velocity and energy. And as soon as you give this heat, these molecules will collide. So the position will change, velocity will change, energy will change. So you have to analyze that. And these properties changes very frequently due to collision. Now if you have to analyze that, this analysis is very difficult. These properties that need to describe the system cannot be measured easily as it is changing frequently. So it is not used in normal scenarios. It is used in very, like when pressure, it is used for high altitudes or rare field theory. There we can, because the number of molecules are very less. The number of molecules are very less. Now, the next approach that we talk about is macroscopic approach. Now, I hope that you already got aware of what is macroscopic. By macroscopic, we will use in normal scenarios, because here we do not focus on an individual molecule. So, for example, this is the system, okay? This system. Now, I have, for example, certain molecules, and when I give heat, their energy is changing. So it is pushing the boundary. Now, instead of studying how one molecule is affecting, how one molecule is behaving, what I will take is, I will take the average behavior of all the molecules. So I do not care. Look, for example, what do you mean by average behavior? Like, see, if this is your system, now one molecule is moving in this direction, one is moving in this direction, there is one more that is moving in this direction, there is one more moving in this direction, one moving in this direction, one moving in this direction, one moving in this direction. So right now, most of the molecules are moving randomly. But if I want to take the average behavior, so you can see here, look, either I can focus on individual molecule, that is microscopic. But what do you mean by average behavior? See, this is going in this direction, this is going in this direction. That means this effect is null, net effect is null. Similarly, this is going in this direction, and let us say this is going, there is one more that is going in this direction. So this and this will have a net effect, 0. Then this is going in this direction, and let us say this is going in this direction. So this will get cancelled. So eventually what we will get is, this is moving in this direction, this is moving in this direction, this is moving in this direction, this is basically, let's say this is also gets cancelled. So now the net effect that I can see, that I have 2 or 3 molecules left that is moving in this direction. So this is the average behavior that I am considering. I am not talking about individual molecule. I am seeing what is the net effect. If I have 20 molecule, how they are moving with respect to each other, I don't care. But what is their net effect? So net effect is yani ki this direction and this velocity. So that is the average behavior. I am not concerned how one molecule is behaving. I am only concerned about how average behavior, what is the average behavior, what is the average velocity, average pressure, average kinetic energy and everything. Okay, so here average behavior of molecule is taken into consideration, neglecting the events occurring at the molecular level. What is happening at molecular level, I do not care. Whatever is happening at molecular level, I do not care. I only care what is happening at the average level. यानी कि how all the molecules are collectively behaving. Okay, and these effects can be perceived by human sense. You can see that, for example, this velocity you can see. Internally what is happening I can't see, but I can see that the system is moving in this direction. Similarly, internally how they are pushing, colliding, I don't know, but what pressure it is applying outside on the boundary, that can be perceived by human sense. Okay, for example, pressure is the average rate of change of momentum due to all molecular collisions made per unit area. What is this? Force per unit area is pressure. Okay, what is the force? Mass into acceleration per unit area. So this is what momentum. Okay, so what is the average rate of change of momentum due to all molecular collisions made per unit area? So now what are the properties? Pressure, temperature, etc. need to describe the system. So all the properties that we see in thermodynamics, for example, pressure is there, temperature is there, okay, velocity, volume is there, what else? Internal energy is there, enthalpy is there, entropy is there. They are all macroscopic properties. Got it? They are all macroscopic properties. ठीक है? Understood? चलिए. Now let us move on to the next part, which is concept of continuum. Now what does it mean? Concept of continuum? So see, okay, see, thank you Raj Ajmira. ठीक है? Now let's see. So now concept of continuum. Now see what is happening here is, let's take one system. Now we have one molecule here and one molecule here, right? We have two molecules, and this is the system dimension, and lambda is the mean free path. Sir, what is lambda? Lambda is the how much distance this molecule can travel, the average distance it can travel before it collides either the system boundary or the another molecule. So you see, it can almost, so can I say that lambda is almost same as length? Because you see, every time, except for very few motions, every time it is able to cross the entire boundary. So if I sum the distance, if I sum this distance, this distance, and I take an average of it, so can I say it is almost equal to system dimensions? Because this is the system dimension. Okay. So I have one condition when lambda is almost same as system dimensions. Okay. Now tell me one thing. That this, so let me remove this first. This molecule can freely move, right? This molecule can freely move. This can also freely move. The distance between molecules is very large. Is very large. Distance between molecule are very large. So see, I am standing, I have this big room. I am standing here, one person is standing on the other corner. I can freely move. I have no contact with the other person. I can freely move. If I move here, I am not going to affect another person. I am not going to affect another person. That means I am a completely separate person. The other person is a completely separate person. My motion or whatever I am doing is not affecting in any way the other person. This is one scenario. What is the another scenario? That now one molecule, let me write it here, very few molecules. This scenario will happen when you have very few molecules, right? Chalo. Now you have so many molecules. You have so many molecules. Now, system dimension is still same. System dimension is still same L. System dimension is still same as L. Okay, but tell me what is the mean free path here. So see what is going to happen here is this molecule will move and collide with the boundary. Collide with the boundary. Collide with another molecule. Collide with another molecule. Collide with another molecule. Collide with another molecule, collide with boundary, collide with boundary, collide with boundary. And the same thing will happen with each and every molecule. Yani ki if one molecule is moving, it is colliding with another molecule or the boundary. So can I say here, mean free path is very less compared to length. Can I say this? Mean free path is very less compared to L. Yes or no? I can say this, right? Mean free path is very less compared to L. Okay? ठीक है, very less. So when will this happen? And it will say that distance between molecules is very low, very small, and it will happen when large number of molecules are there. When large number of molecules are there. Okay, ठीक है, इतनी अब this much we have understood. Now see this. Now just imagine this scenario. In this room there are 50 people. Earlier there were only 2 people. So whatever I am doing is not affecting him. I can move. I am not pushing anyone. Okay, but now imagine this. In this room there are 50 people, and this side I have another person, this side I have another person. In my front side there is one more person, in my back side there is one more person, and then there is another person after that, here also this side there other. Okay, chalo. So if I move like this, I am going to push the other person away. If I move like this, I will push the other person on the other direction. If I move forward, I am going all the people in the forward direction. If I am moving backward, I will move all the people in the backward direction. That means whenever I am moving, I am affecting the molecules that is just beside me, or this side, whatever it is. And this molecule is going to affect the another molecule that is beside that. So that means if you do any disturbance with the system, or for example, if you come and push one person or one molecule in the system, it is going to affect everyone. So they are all joined, they are all continuous. Look, molecules are separate molecules, but they are acting like a continuous medium. Here also we have 2 molecules, but they are not acting as a continuous medium. But here, why they are not acting as continuous? Because they are not affecting. one another. You can come and push anyone, it is not going to affect the other person. But here, in this case, in the second case, if you are pushing one person, it is affecting everyone. It is affecting everyone. So if you, what is continuous medium? For example, water is there. If you go and like rotate your finger in the water, so only one layer of water will move or everything will move. If you keep doing this, for example, water is there and you put your finger like this and you rotate this, so only that layer will move or the whole water will keep moving. After some time you will see whole water will keep moving. Why? Because water acts as a continuous medium. Molecules are very close to each other. Similarly, if molecules are very close to each other and you disturb one molecule, it is going to disturb another molecule because that is just beside him. It will transfer its energy to another molecule. That will transfer its energy to another molecule. Then it will transfer another molecule. So it will be a continuous phenomena that will happen one after other. And that is why this kind of system is called as continuous medium. And it says that this type of system is following concept of continuum. So what is the condition? This condition. Your lambda should be very less compared to the system dimensions. Then you can say that your concept of continuum is valid. Concept of continuum is valid. Are you able to understand this point? So it is saying, from the macroscopic viewpoint, always understand, when we say macroscopic means large number of molecules. Because if large number of molecules are not there, you will not use macroscopic approach. You will use, if few molecules are there, you will use microscopic approach. Okay, large number of molecules. So from the macroscopic viewpoint, we are always concerned with the volumes which are very large compared to molecular dimension. Means volume is length, system dimension, and it is very large compared to molecular dimension, means mean free path. So whenever large number of molecules are there, I told you already, large number of molecules, yani ki this condition will be valid. This condition will be valid. So disregarding the behavior of individual molecule, when the matter is treated as continuous medium, it is called as continuum. It is called as continuum. And the concept of continuum is valid when the system dimensions are much larger than mean free path of molecule. Then mean free path of molecule. ठीक है? So sir, you are saying when system dimensions are much larger than mean free path. But how larger? There is a number or not? Yes, there is a number. So that is called, what gives you this parameter that concept of continuum is valid or not is given by Knudsen number. So Knudsen number is basically mean free path by L. Mean free path by L. And see, concept of continuum will be valid when L is much greater than lambda, yani ki denominator is much higher. Denominator is much higher than lambda. That means for concept of continuum, for concept of continuum to be valid, lambda length should be much greater than lambda, and Knudsen number, which is defined as lambda by L, it should be much less than 1. But how less? How much? So it is given by this. If Knudsen number is less than 0.01, if Knudsen number is, yani ki if it is, let us say 0.01 is the minimum that, it is the maximum that can happen, okay? If it is less than lambda by L. So that means if your lambda is less than 0.01 L, or you can write length is greater than 100 times of lambda. See, if this is your system, if this is 100 So your mean free path should be 1, not more than 1. It should be 1. Even this is much, it looks more than, I can't show it like this, but even this is much greater than 1. Okay. So 1 will be like a point. If this is your molecule, it can just move a little bit. That is your system dimension. It looks like a point only. Then in that case only, you can say that concept of continuum is valid. So if this condition is satisfied, then you can say concept of continuum is valid. But if it is greater than 0.01, that means concept of continuum does not hold good, yani ki it is not valid. It is not valid. Then what will happen, sir? Then these cases you study in fluid mechanics. Ki sir, if it is in this range, 0.01 to 0.1, it is called as slip flow. 0.1 to 10, it is called as transition flow. And if it is lambda is greater than 10, it is called as free molecular. So this is the case I was telling you here. This is the case I was telling you. You see, it is free molecular. Molecules are free to move. They can move wherever they want. It is not affecting anyone. So you can call this as, when Knudsen number is greater than 10, you can call free molecular flow. Got it? Did you got my point? Yes or no? Yes. आगे चलें. चलिए. Now, so many times we are saying, sir, system. What is system? What is system? Okay. Every time. This is the word that you are going to hear like 1,000 times in thermodynamics. Every question, every topic, every concept you are going to hear, sir, system. So what is system? So guys, and a lot of students do this mistake. They keep a close mind about system. Sir, what does that mean? It means that, like they are very obvious about system. Ki, sir, this is my system. For example, if I give you one example, ki, okay, this is my piston cylinder arrangement. And we have a gas here. Okay. Now tell me what is the system. Now tell me which one or what is the system. So 99.99% of the student will tell ki, sir, this is your system. This, yani ki whatever is there inside the blue boundary is your system. And whatever outside the blue boundary is surrounding. Whatever outside the blue boundary is surrounding. 99.99% of the student will answer this. And 0.1% will have no answer about this. Okay. Chalo. Now why is that? Because you always keep a close mind about system. See, there is an entropy question. Ki calculate if system is transferred, leave system, if gas is transferred 100 kilojoule of heat, then find out the entropy change of the reservoir. That means there is a reservoir that is supplying some 100 kilojoule of heat in the gas. And when you start calculating the entropy, now according to you it is a surrounding, not system. But when you find out entropy of reservoir, for this case, this is your system. This is your system. Sir, it is very confusing. Why are you confusing us? We always know that gas is the system. No, that is not true. But it is true 99% of the time. But the truth is that you do not have to keep a closed mind about system. You have to open your mind with respect to system. Let us discuss this in very detail. Okay. Why I am saying you need to keep an open mind about system. See, there is one cycle, thermodynamic cycle, that you will study later, that is called as Rankine cycle. Okay. And Rankine cycle has a boiler. It has a turbine. Turbine gives you work output. Here I give heat. Then this is my condenser. From condenser, heat is rejected. And here I have pump. Work, input. हेलो निर्मल, हाय. ठीक है, चलो. तो सी, आई एम सिटिंग इन द इन्वेंटरी डिपार्टमेंट. ओके, वो कोल आता है ना, वी हैव इफ आई हैव अ थर्मल पावर प्लांट, so we order coal, mostly a fuel or something. So let us say I am sitting in the inventory department. I want to know how much coal is required to produce some, let's say 10 gigawatt of energy, of electrical power, because I have to order it, right? So I want to know how much coal should be burned to provide this much amount of heat. So my focus is, whatever I do, I need to continuously provide this much amount of heat in the boiler. Because if I am able to provide this much heat, only then work will be produced, and this work will be transferred to generator, and electrical energy will be produced. Okay. So right now my focus is boiler. How my boiler is working, what is the efficiency of the boiler, is there a moisture problem, is there a, all the steam pipes are working properly, in which water goes up and converted to steam, all the fire plug, all the superheater, reheater, everything is working properly or not. Because boiler is very big in power plants. There are so many components in boiler which we study in detail. But basically my concern is boiler. How my boiler is performing, because I need to supply a given amount of coal to produce this much amount of heat. So my interest is boiler. So for me, boiler is my system. For me, boiler is my system. But let us say you are sitting in the production department, the distribution department, electricity distribution you have to do. So you need to know how much work output you are getting from here. So that, because this work output will be converted to electrical power. This work output will be converted to electrical power. Now, if you want to distribute electrical power, you need to know how much work output is coming from turbine. And whatever you do, you need that much work output. So you need to make sure that your turbine is working properly. So for this person who is sitting in the distribution department, for him, turbine is a system. These are two different people. For one, boiler is a system. For the other person, turbine is a system. Now these people do not fight कि no, how can boiler be your system? Bhaiya, it depends on your requirement, your focus. Nirmal, we are covering the basics here. Okay, so I am trying to cover whatever is possible in 4 classes. Okay, and then we will have, uske baad FM will start, and then later on we will try to come up with the next chapter basically. Okay, this is the objective right now. Okay, so what I am trying to tell you here is that the person who is responsible for heat generation or coal production, coal, buying of coal, for him the focus is different. So for him the system is different. The person who is sitting in distribution department, for him focus is turbine. So for him turbine is his system. Similarly, someone is sitting in environmental department, compliance department. This much heat is going, CO2 is going in the environment. So he need to know what is the exhaust coming out of condenser, because this will be exhausted to surrounding. So he is concerned what is coming out of condenser. So for him, the person who is sitting in the compliance department, for him condenser would be a system. So the definition of system varies. A lot of students are just focused on one thing. Okay, this is my system. Now everything else is my surrounding. And they start fighting with the other people. No, how can you assume this is a system? So Baba, there is nothing like there is no fixed definition of system. Right now, whatever is your focus, that is your system. Everything else is surrounding. So if you choose boiler as your system, everything else is a surrounding. If you choose turbine as your system, everything else is a surrounding. If you choose condenser as your system, everything else is your surrounding. You can also choose boiler and turbine as your system. Now this is your system. Now everything else is surrounding. Everything else is surrounding. So the thing is that it depends on what is the requirement. Based upon your requirement, you will choose a system. And once you have chosen the system, everything outside that is surrounding. And system and surrounding will be separated by a boundary. So let us say if I choose this as my system, then everything else is surrounding. So this is surrounding. And system and surrounding are separated by a boundary. And everything consisted of, like if you talk about everything here, it is called as universe. Got it? So first you have to choose a system very carefully based upon what is your requirement. Then once you have fixed your system, then surrounding is automatically defined. And the boundary that separates system from surrounding is called as, or the layer that separates system from surrounding is called a boundary. And when everything is combined together, it is called as the universe. Okay? Now there are few things I need to know about the boundary. There are few things that we need to know about the boundary. So see, it is a surface through which system and surrounding interacts. So see, let us say this is my system. And this is my surrounding. Now, what do you mean by interaction? If I am sitting in this room and someone is sitting outside the room, then how will we interact? ठीक है, बोल के कर सकते हैं लेकिन molecules do not speak, right? So if I want to interact, यानी कि if I want to exchange energy or if I want to exchange mass, so how will I interact? I am sitting inside, someone is sitting outside. Okay, so I am sitting here, someone is sitting outside. How these two things will interact? These two things will only interact when it crosses the boundary. If I am sitting here, I cannot interact. Let us assume interact means you are touching someone basically. Okay, so if I have to touch someone who is sitting outside, I have to cross the boundary of my room, and then only I will be able to interact with that person. So if system and surrounding has to interact, that means whatever is there in whatever form, for example, if I am interacting in the form of touch, if I am interacting in the form of touch, then my hand should go outside. If I am interacting in the form of sound, then my sound should go outside. Similarly, in whatever way system and surrounding are interacting, that thing should cross the boundary. In whatever way system and surrounding are interacting, that must cross a boundary. If that thing is not crossing the boundary, you will never be able to say that interaction has happened. You have to look at the boundary. Okay, if this is crossing, then only you will say that interaction has taken place. यानी कि system and surrounding have interacted. Okay. Now system and surrounding can interact in two ways. Mass, we will study that in very detail. I am just giving you a brief right now. Mass and energy. So either some mass will be coming from surrounding or some mass will be going out from system. Or energy, यानी कि some energy will be going out from system to surrounding or some energy will be coming in. So mass or energy. Mass or energy. Okay. So basically, system and surrounding will interact either in the form of mass or in the form of energy. If it is interacting in the form of mass, then mass must cross the boundary. If it is interacting in the form of energy, then energy must cross the boundary. यानी कि whatever is interacting must cross the boundary. That is the ultimate thing. If it is not crossing, for example, mass is moving from here to here, that means system and surrounding are not interacting. Or for example, mass is moving from here to here, that means system and surrounding is not interacting. As long as mass will not move, cross the boundary, that means system and surrounding are not interacting. They are not interacting. Now, based upon this interaction, boundaries can be of many kind, can be of many types. First is, boundary can be real or imaginary. Boundary can be real or imaginary. So what do you mean by real and imaginary? You see, for example, one pipe is going like this. It is a 3-kilometer pipe, okay? And water is flowing like this. Now you want to analyze how the properties of water are changing. So of course you will not analyze the whole 5-kilometer or 3-kilometer pipe. What you will do is, you will fix a volume here. For example, you will draw a boundary like this. And now you will do your analysis across this boundary. So this is your system right now. And everything outside your system is surrounding. So this is surrounding, this is surrounding. And you can see here that mass is crossing the boundary. You see, and mass is also coming out. Similarly, energy could also be, for example, you are giving heat, so energy could also be crossing. Now, as you can very clearly see here, this is a real boundary, okay? This is a real boundary. But this is actually not a real boundary. It is an imaginary boundary. It is a imaginary boundary. It is not an actual boundary. It is an imaginary boundary. Okay, it is an imaginary boundary. So that is how you can classify boundary as real or imaginary. Sometimes boundary is not actually there, but you just imagine for your analysis, you assume that we have an imaginary boundary and we see across the boundary. Okay, this is my boundary. Is mass crossing or not? Is energy crossing or not? So see, heat is crossing through a real boundary, but mass is crossing through an imaginary boundary. Okay, so boundary can be real or imaginary. Real boundary is shown by a continuous line. Imaginary boundary is shown by a dotted line. Okay. Now boundary can be fixed or movable. Boundary can be fixed or movable. What do you mean by that? So you see, you take a fixed container. You take a fixed container and let us say there is some gas here. Now you are heating it. Now see, whatever you do, you heat it, how much ever heat you want to give, this boundary will not change. The shape of the boundary will not change. So it is a fixed boundary. It is a fixed boundary. But if you take a piston cylinder arrangement, this is your piston and piston can move in this direction. Okay. And let us say you have some gas. Now, if you transfer some heat to the gas, then what will happen? Right now, see, what is my boundary? Right now, this is my, I don't know if you can see this color. Let me take some other color. Okay, red. You can see this is my boundary right now. But when you start giving this heat, so molecules energy will increase. It will start moving. It is going to push the piston. It is going to push everything, but other boundaries are fixed. Only piston can move. So it is going to push the piston forward. So when it will push the piston forward, so what will happen is piston will come here and the boundary will change to this. Now this will be your boundary. So as you can see, your boundary is changed. So this is called as flexible boundary. Flexible boundary. So, or movable. You can also call it flexible or movable boundary. So this is how you can classify boundary. Boundary can be real. There is actually a boundary, or boundary can be imaginary as well. Just for your analysis, you have assumed an imaginary boundary. Boundary can be fixed. That means whatever you do, your boundary will not change. Boundary can be flexible as well. So that means if you are disturbing your system, the boundary will change. So it can be flexible. Okay. So this is how boundary can be classified. Okay. Now we will talk about types of system. So we'll talk about types of system based upon the energy interaction. But this is what we are going to talk tomorrow, not today. So a system and surrounding can interact with two ways. I told you already, system and surrounding can interact either in the mass form or in the energy form. Mass form or energy form. Okay. So mass transfer or energy transfer. Now based upon this interaction, we can classify our system into closed, open and isolated. And based upon the state of system, state means solid, liquid or gas. Based upon the state of system, we define our system as homogeneous and heterogeneous. So this we will talk tomorrow. We will start with closed system and then we will move ahead. We will understand because time is not enough, so I will not be able to explain. I mean, I can explain it quickly, but there is no point. We'll try to come up with few examples. We'll try different things. Okay. So we will start with this tomorrow and we'll talk about systems and a little bit of Gibbs phase rule, pure substances. Tomorrow we will talk about that. Okay. So I think we can stop here. I hope that you enjoyed the session. If you have enjoyed it, give it a like. Okay, quickly. And I will see you tomorrow at the same time. So do not miss the class, guys. Come live classes. Okay. Try to attend live classes. Okay. Chaliye. So I will see you tomorrow at the same time. We'll start with the types of system. Okay. What are different types of system?